Hey everyone. So in this video I like to talk about vectors and direction. So in our last video on vectors we introduced the idea of a vector and we focus mainly on the component form of a vector. Right, so here let's say I've got some vector v. Right, so the component form of the vector really just describes the horizontal displacement of this vector and the vertical displacement of this vector. And so if I label the horizontal displacement A and the vertical displacement B, then our vector V can be expressed as, these horizontal and vertical components together. So in angled brackets, we write A comma B. That's one way we can represent this vector. And then we also said that another way we can represent this vector is in terms of sort of the most basic vectors, the horizontal and vertical vectors of length 1, right? So here we usually call these I and j. So here I is the horizontal vector of length 1 in the direction to the right, and j is the vertical vector of length 1 directed upwards. And so here, this vector with horizontal component A and vertical component B can be expressed as A times I, right? A units in the left or right direction, and plus B times J, so B units in the up direction. And so in this video, I like to change our direction a little bit and focus on this idea that a vector really is representing a distance and direction, right? So we said a vector is a line segment with direction, and so there's really two pieces of information in there, distance and direction. And so I'd really like to focus on these parts of a vector. So here, when I say distance, we might call that magnitude. And when we talk about direction, we might be talking about an angle. And so the way the magnitude and the angle of a vector are related to the components of a vector, or the horizontal and vertical components of a vector, really via the sine and the cosine function. And so if I draw out my vector v again, so here's my vector v, and I draw out the horizontal and vertical components, and again label them A and B. And let's say, I want to also include this angle of my vector, so I might put that angle down there, kind of thinking of my angle in standard position. So there's my angle theta. Well here, how are all of these different quantities related, the magnitude, the angle, A and B? Well, they're related by sine and cosine. If I write down cosine of theta, well, cosine of theta, if I kind of remember my right triangle trigonometry, it's the adjacent side to our angle theta, the side next to it divided by the length of the hypotenuse of this right triangle here. And so here, it's not divided by v, but it's divided by, maybe I'll write this as the magnitude of v, if I'm really trying to think of that quantity as a length. And so here, cosine of theta would be A, the horizontal component of our vector, divided by the hypotenuse of this triangle, that's the length of the vector, so the magnitude of v. Right, and so here I can sort of shuffle these terms around. I can multiply both sides by the magnitude of v. That's really just a number. It's the length of the vector. It's the hypotenuse in this triangle. If I multiply both sides of this equation by that number, we get that the magnitude of v times cosine of theta is equal to A. Right, so here where A is our horizontal component. And we can do the exact same thing to relate the vertical component to our angle and the length of the vector. Right, so here if we instead take sine of theta, well then we're going to take the opposite side length and divide it by the hypotenuse. And so this gives us b, the vertical component of the vector, and then that's divided by the length of the vector, so that's the magnitude of v. And again, we can move some terms around, multiply both sides by the magnitude of v, whatever number that is, and we get the magnitude of v, the length of the vector, multiplied with sine of theta, is exactly the horizontal, the vertical component of the vector. And so this gives us a way of, if we have the magnitude, so if we have the magnitude and if we have the angle, this gives us a way of finding the horizontal component or the vertical component. Right, so this is really telling us if we have the magnitude and we have the direction of the vector, we can find the component form of the vector without too much difficulty using these sorts of formulas. So maybe I'll label this here. This is to go from the magnitude and angle to the component form of the vector. And so one thing I should add is that this is identical, this is completely the same process to finding, to going back and forth between polar coordinates and rectangular coordinates. So here I should write, this is identical to converting from polar coordinates to rectangular or Cartesian coordinates. Right, so remember here, maybe I'll just quickly do a little bit of a recap of this. If we have a polar coordinate, a point in polar coordinates, right, so a point in polar coordinates is labeled by a distance and direction from the origin. So maybe here, I'll have some point, let's say out here. So here, this point is given by a distance, r, and an angle, theta. Right, again, the idea is that there's this triangle that fits into our picture. And if we wanted to figure out what this point is in terms of x and y, in terms of the horizontal and vertical coordinates of this point, well then how do we do this? Well, again, we do the same exact ratio, right? We say that, well, cosine of theta is equal to x over the length of the hypotenuse, x over r, and we would multiply both sides by r to get r times cosine of theta is equal to x. And similarly, we could take sine of theta is equal to y over r to get that r times sine of theta. If we multiply both sides by r times sine of theta is equal to y. And so here we get really the exact same formulas, the exact same relationships, and it's really the exact same picture. It's just we have some different names in the parts of our formula when we're talking about vectors, because when we're talking about vectors, we're sort of using slightly different terminology, but really it's the same picture, the same formulas. So you don't have to remember these as two different things. Really, these are the identical ideas. So let's use this idea to find the component form of the vector v that has a magnitude of the square root of 3 and an angular direction of 300 degrees. Okay, so here if I kind of draw out a coordinate plane, and if I imagine my vector with the initial point at the origin, right, the position of the vector doesn't matter, so I can imagine the vector anywhere I want. Maybe I'll imagine it at the origin. Well, it's got an angle of 300 degrees. So 300 degrees, that's 60 degrees shy of a full 360-degree rotation. And it's got a length of the square root of 3. So here, this is my vector v. And here, I should note that the magnitude of v is the square root of 3. Okay, so this is a picture we should have in mind for our vector. Now, how do we find the components of this vector? Well, here we want to find the vertical component and the horizontal component. And here, here's our angle theta. Well, if this is labeled A and this is labeled B, we said that A is equal to, here this is the magnitude of V times cosine of theta. And then here B is equal to the magnitude of V times sine of theta. Right, so these are just the cosine and sine ratios, but here multiplied both sides of our ratio equation by the magnitude of V. And so here if we want A, well, we know the magnitude of V, we know it's equal to the square root of 3. And then cosine of theta, well, theta in this case is 300 degrees. Right, and so here, maybe let's use our unit circle to evaluate cosine of 300 degrees. But this is an angle which results in, let me draw this a little bit better. This results in a 30, 60, 90 triangle, 60 degrees from the horizontal axis, right? So here we can kind of imagine a 60-degree angle here. And so this is giving us a triangle with a short side length of 1/2, a long side length of the square root of 3 over 2. But that's a y value. It's in the negative direction, so I'm going to label that negative square root of 3 over 2. And so here this tells us that A is equal to the square root of 3 times cosine, right? Cosine of our angle, and that's 1/2. This is the square root of 3 over 2. And then B, well, this is the square root of 3 times sine of 300 degrees. And sine of 300 degrees is going to give us that y coordinate on that unit circle. That's a negative square root of 3 over 2. So this is telling us that B is equal to, well, it's the square root of 3 times negative square root of 3 over 2. And this can be expressed as, well, the square root of 3 times the square root of 3 is just 3 itself. So this is negative 3 over 2. So maybe I'll go back to our picture up here, replace A and B with the square root of 3 over 2, and this is, what is this? This is minus 3 over 2. And so those are our components of our vector, right? So here this is telling us that V, our vector V, can be written in component form as this is the square root of 3 over 2, comma, negative 3 over 2. And so one thing I like to add is that here our pictures, they're really almost identical. They're sort of the same, a very identical looking right triangle that we've drawn for our vector and for our unit circle. And really these triangles, they're similar to one another. One is just stretched from the other by a factor of the square root of 3, right? So this triangle that's in our vector, it's really just the same as the triangle in our unit circle, stretched, all the side lengths stretched by a factor of the square root of 3. So let's do the same thing and find the component form of the vector with magnitude and angle 8 and 220 respectively. And so here if we draw out our vector again, with the initial point at the origin, well, 220 degrees, that's 40 degrees past 180, or this is the same as 40 degrees plus 180 degrees. And so here I can imagine my angle being maybe about there, 220 degrees. And our vector looks something like this. And so here, this is our vector W with a magnitude of 8. Okay, so maybe I should expand my axes a little bit, and we want to sort of include the picture of our triangle here. And we want the horizontal and vertical components of this vector so that we can write this vector in component form. And so if A is equal to the magnitude of W times cosine of theta, well, this is equal to 8 times cosine of 220 degrees. And now, 220 degrees, right, it's 40 plus 180. It's not one of our special angles, right? 210 would be special. It'd be 30 degrees past 180. We can imagine a 30, 60, 90 triangle pictured to our right, but that's not the case here with 220 degrees. And here, if we had maybe 225 degrees, that would be a 45 degree angle on top of a 180 degree angle, and we'd be dealing with a 45, 45, 90 triangle. But again, that's not the case. We might have some techniques for evaluating this exactly, but I think it's a little bit more work than necessary right now. Really, let's just evaluate this using a calculator. And so here this is approximately, if we take 8 times cosine of calculating 220 degrees, make sure your calculator is in degrees mode, we get approximately negative 6.1283. And then b here, right, so sine is the ratio b over the hypotenuse, the length of our vector. And if we multiply both sides by the length of our vector, we get that b is equal to the length of our vector times sine of theta, which is equal to, b is equal to 8 times sine of 220 degrees. And this is approximately, it comes out to be negative 5.1423. And so this is telling us that our vector, if we write it in component form, maybe I shouldn't write equals, I should say approximately, this is negative 6.1283, comma, negative 5.1423. So in our previous 2 examples, we started with the magnitude and the direction of a vector, and we use this to find the component form of the vector. We had these formulas for a and b using our sine and cosine functions. But what if we wanted to go in the other direction? What if we started with the component form and we wanted the magnitude and the direction of our vector? How do we do this? Well, here, maybe let me sketch out this information, right? So here's our vector v, and here's the horizontal component, and here's the vertical component that we're assuming that we already know, right? Let's say we started with the component form of the vector, we know a and b, and we want the magnitude and the angle. Well, we've already talked about how to find the magnitude of this vector, right? So the magnitude of this vector, the length of this vector, is just the hypotenuse in this right triangle. And so we can just use the Pythagorean theorem that a squared plus b squared is the hypotenuse squared. In other words, the square of the length of this vector. And so if we take the square root of both sides, then we'll just have the length of this vector is equal to the square root of a squared plus b squared. Right? So the sum of the squares of the leg lengths. And so that's the magnitude. But now how do we find the direction or the angle of this vector? And so the main way we go from side lengths of a right triangle to an angle is using inverse trig, right? So trigonometric functions take an angle, give us ratios of the side lengths. Inverse trig does the reverse. It takes in ratios of the side lengths and gives us back an angle. And so here, if we start with the component form of the vector, if we start with a and b, what trigonometric function works with these side lengths a and b? Well, a and b, they're the adjacent and opposite sides of this right triangle with respect to our angle theta. And so the trigonometric function that relates the adjacent and opposite sides to our angle theta, well, that's the tangent function. So we can use tangent, or inverse tangent actually, to obtain the angle. Right, so tangent inverse of, tangent takes an angle and gives us back the opposite divided by the adjacent side length. And so if we take tangent inverse of the opposite divided by adjacent side length, we'll get an angle. But we'll only get an angle that works, that gives us b over a, between negative 90 degrees and positive 90 degrees. Right, so remember that when we use our inverse trigonometric functions, they only give us back angles in certain windows, for certain intervals. And the tangent function is only going to give us back angles between negative 90 and positive 90 degrees, or in other words, on the right side of our unit circle. And so if our vector is pointing to the right, then tangent inverse of b over a is going to give us our angle. But if our vector is pointing to the left, then really we'll have to add on pi, or 180 degrees, to get the correct angle. Right, maybe just to really draw a quick picture, if our vector is angled out here to the left, then tangent inverse, right, it's going to give us back an angle with the same slope. And so it would give us back this angle down here. And so here, tangent inverse, all this to say that tangent inverse of b over a is equal to theta if the vector is directed right and it's equal to, well here, we would need to add on 180 degrees, or look at the opposite side right here. If we add on 180 degrees, we'd be looking at the correct vector now. So tangent inverse of b over a plus 180 degrees is equal to theta if the vector is directed left. So hopefully these conditions or these ideas aren't too confusing. This is really just, it's the same ideas we've been dealing with when we've been solving equations and when we've been working with trigonometry involving our inverse tangent, or just our inverse functions in general, is that we have to be aware of where our angle is actually positioned, what quadrant it's actually in, and so we have to be conscious as well when we're dealing with vectors. So here we're given two vectors in component form, and we want to find the magnitude and the angle of these vectors. So let's start by finding the magnitude of the vector u. And so the magnitude of a vector is just, here using the Pythagorean theorem, it's the square root of the square of the horizontal component added on with the square of the vertical component. And so squaring the horizontal component, that's 1, and squaring the vertical component, that's 3. So we get that the magnitude of the vector is the square root of 4, which is equal to 2. And so how do we find the angle of this vector? We can use inverse trig, but actually let me just draw out the picture real quick just to really give us some intuition of what's going on with this vector. So here, maybe I'll start by drawing the coordinate plane. And so we said that the horizontal component of this vector, that's -1. And the vertical component of this vector, that's negative square root of 3. And this vector here is drawn like so. So this is our vector u. And what we've just identified is that the magnitude of u, using the Pythagorean theorem, is 2. The length of this vector, the length of the hypotenuse of this right triangle here. And so, before we resort to using inverse trig, I want to just notice here that this is actually a very familiar looking triangle, right? I see the square root of 3 here. I see that the short side length is half of the hypotenuse side length. This looks a lot like our 30, 60, 90 triangle, but just stretched. Right? So this is the short side length. This is -1/2, but multiplied by 2. Right? This long leg length, this is negative square root of 3 over 2, but just multiplied by 2. And then this hypotenuse, well, this is just 1 multiplied by 2. This is our 30, 60, 90 triangle that we see in our unit circle, but just stretched by a factor of 2. And so this is saying that we've got a 30, 60, 90 triangle here, where this is this is a 60-degree angle, this is a 30-degree angle. And so here we're looking at an angle that's 60 degrees past 180. Or in other words, our angle, or direction of our vector, is 240 degrees, right? 180 degrees on top of 60 degrees. It's 240. That's the direction of this vector. And if we would have used inverse trig, for example, inverse tangent of our side lengths of b over a, so negative square root of 3 over -1, we would have taken inverse tangent of the square root of 3. Right, so we would have gotten inverse tangent of negative square root of 3 over -1. We would have gotten inverse tangent of the square root of 3 to find our angle, this would have given us 60 degrees. Right? It would have given us this angle here. And so because our vector is pointed to the left and not to the right, tangent inverse is not going to give us the correct angle. It's going to be off by 180 degrees. Right? We would have had to add 60 and 180 degrees together to get our correct angle, and that's what we did here. Okay, so now let's look at this next example. Here we have a vector in component form, but in terms of the length 1 vectors I and j. And so we can again use the Pythagorean theorem to find the magnitude of v. Here this is the square root of -3 squared plus 4 squared. And this gives us, the square root of 9 plus 16. This is the square root of 25. And the square root of 25, that's just 5. So we've got the magnitude of our vector v now. Now what's the direction of our vector? And so let's again draw out a picture. Here's my coordinate plane. Right here we're saying that the horizontal component, that's -3. It's -3. And the vertical component is 4. And then here, if I draw the vector, and what did I label this vector as? I called it W, I think. Let me double check. No, I called it V. So this is V. We said that the magnitude of V, this is equal to 5. So there's just a 3, 4, 5 right triangle in this picture here. So what's the angle of our vector? So it's this angle here. This is the direction of our vector. Now this isn't one of our special right triangles that we know the angles of. So here we do have to resort to using inverse trig. And so here we can use tangent inverse of, well, the opposite side length divided by the adjacent side length. So right, -4/3. And so again, tangent inverse is going to give us an angle on the right side of this unit circle. Right, so tangent inverse is going to give us an angle with the same slope on the right side of this unit circle. It's going to give us this angle down here. Right, so this is tangent inverse of -4/3. And we haven't actually evaluated with a calculator yet what that is, but I know that pictorially this is what we're going to get. And so if I want the actual angle of the vector, I'm going to have to add 180 degrees onto this purple angle. And so here, tangent inverse of -4/3. Did I do this ahead of time? So I did. This is negative, maybe I should not write equals, this is approximately -53.13. And so our angle theta is, again I should write approximately, -53.13 degrees plus 180 degrees, and this is approximately 126.87 degrees. So this is our direction of our vector v. So let's apply these ideas of the distance and direction interpretation of a vector to some more realistic problems. And so one idea that can be modeled by vectors is the notion of the velocity of an object. So the velocity of an object is just the object's speed paired together with its direction of motion. So here this idea, this can be modeled with vectors. Right, so here, the object's speed, this can go along with the magnitude of the vector. The magnitude of the vector can represent the speed of the object, and the angle of the vector can represent the direction of motion. Right, so for example, let's say I have some runner, and let's say they're running 8 miles per hour in a particular direction. Well, here I can think of this length of this vector of being 8 as representing the 8 miles per hour. And then here the direction of the vector is telling me which direction this runner is running. Or maybe I can think of someone is swimming across some body of water. So maybe they're swimming in this direction here. And maybe they're swimming at, let's say, 2 meters per second. And so here, the length of this vector being 2 is describing the speed at which this swimmer is swimming, and the direction is telling us which way they're going. One thing I should add when it comes to these problems involving vectors and velocity is that sometimes there'll be multiple velocities that are interacting with one another. So for example, maybe this swimmer, it's swimming in a body of water that's moving. Let's say the water is moving, let's say, in this direction at a speed of 1 meter per second. So it turns out that the direction that the swimmer actually travels is going to be the sum of these two vectors. So here, if I imagine drawing that vector, that 1 meter per second vector in the direction that goes off to the right, if I draw it at the very tip of our green vector representing the swimmer's velocity, how the swimmer actually travels, the true velocity of the swimmer comes from the sum of these two vectors, right? So here if I call this vector u, is our green vector, and v is our blue vector, then u plus v, this is the true velocity of the swimmer. So the direction in which they'll travel and the speed at which they'll travel after the influence of the current of the water in which they're swimming in. So let's take a look at this problem here where we can apply this idea of vectors representing velocity. So here it says, suppose a plane is traveling north at 300 miles per hour and experiences a 40 mile per hour crosswind at an angle of 60 degrees. And so we want to find the true speed and the true direction of the plane, in other words, the speed and the direction of the plane after it's been influenced by this 40 mile per hour crosswind. So I'd encourage you to pause the video and try and just sketch a picture out here that can represent this situation. So try and draw a picture using vectors that incorporates the velocity of the plane and the velocity of the crosswind. So here, if we draw a coordinate plane, right, so the axes can tell us or can represent the different directions possible, right? So in the north, south, east, and west, the directions we might see on a compass. And so here, this plane that's traveling north at 300 miles per hour, this can be represented by a vector. Right, so here maybe I'll call it the vector u. And so 300 miles per hour, that can be the length of our vector. Right? When we use vectors to represent velocity, the length of the vector is the speed of the object. So here 300 miles per hour. And then again, it doesn't matter where we place the vector. The vector's position doesn't matter, just the distance and the direction of the vector. And so maybe I'll draw the vector here. So here, this vector, it's traveling directly north, so directly up this coordinate plane. And here, the length of the vector, I can think of it as 300, and it's representing 300 miles per hour. So this is our vector u. But then we also have another vector here, right? We have this vector corresponding to the crosswind that's going 40 miles per hour. And it's telling us the angle of this vector is 60 degrees. And so here, 60 degrees might look like so. I can do a better job of that. It might look something like this. And so here, maybe that's a 40 mile per hour, length 40 vector representing the crosswind. And so this crosswind is happening, sort of all over the place. And it's sort of pushing this plane. And so here, what's the true, the vector that represents the true speed and direction of the plane? Well, it's obtained by taking the sum of these two vectors. So if I kind of imagine sort of stacking these two vectors on top of one another, sort of connecting the tip and the end, well then the sum of these two vectors, that's this new vector here. And so here, if this vector is represented by v, then this red vector representing the true velocity of our plane, that's u plus v. And if we can find this vector, we can find the true speed and the true direction of the plane. And so here, let's start getting some component forms of our different vectors, and let's add them together to get our u plus v vector. So here, u, this is our plane. And so here I'm going to write this in component form, but I'm going to use the form of I and j are sort of basic vectors of length 1. So here, this vector, it's traveling directly north 300 miles per hour. So here this is saying that the horizontal component of our vector is 0. That's not j, that's I. And the vertical component of our vector, well, that's 300. And this vector is traveling directly north, so the vertical component is the entire distance of our vector. 300, in this case, miles per hour is what it's representing. And then our vector v, right, so this is some sort of component form. We don't know the values a and b, but we know how to get a and b from our magnitude and direction, right? We said that here, remember that a is equal to the magnitude of v times cosine of theta, and b is equal to the magnitude of v times sine of theta. And so here, what does that mean a is equal to? Well, we said that a, I'll rewrite this out, so v is equal to a, we said that that's the magnitude of the vector, that's 40 miles per hour, times cosine of 60 degrees. That's the angle of our vector. That's the horizontal component. And we can add this with the vertical component. So 40, the magnitude of the vector, times, this is sine of 60 degrees. And this is times our vertical component vector, j. And so here, 40 times cosine of 60, well, cosine of 60, what is this equal to? This is 1/2, right? So this is 40 times 1/2 I plus 40 times, well, sine of 60, that's the square root of 3 over 2 times j. And so here we can rewrite our v vector as 20i plus square root of 20 to the square root of 3, 20 times square root of 3, j. So we have one vector, we have our component form of our v vector, our crosswind vector. We also have the component form of our plane vector prior to influence from the wind. And we're saying that after influence from the wind, the true velocity vector is obtained by adding these two together. So here we're going to add the different components of our two vectors. So 0i plus 20i, so here I'm going to write u plus v. This is equal to 20i. And then here if we add the vertical components, that's 300 plus 20 square root 3, so this is plus 300 plus 20 square root 3 times j. So this is the component form of our u plus v vector, but now we want the direction, so the angle, and we also want the magnitude. So how do we find the magnitude of u plus v? Well, the magnitude of u plus v is equal to, applying the Pythagorean theorem, we get 20 squared plus the square of the vertical component, that's 300 plus 20 square root 3 squared. And so Here, I'm just going to run this through a calculator. I don't think we're going to get something all that clean out. So here, this gives us approximately 335.2. And then here, the magnitude of u plus v, this is supposed to be the speed of the plane after influence from wind. So this is miles per hour is what this quantity is representing. And then here we can use tangent inverse to find the angle of our vector. So this is tangent inverse of, well, we would take the vertical component, 300 plus 20 square root 3, divided by the horizontal component, right? So this is 20. And so if we take inverse tangent of this vertical side length divided by the horizontal side length, tangent inverse gives us an angle. And because this vector is leaning to the right, tangent inverse will give us the accurate angle of this vector. And that ends up being, I guess I shouldn't say equal to, this is approximately 86.6 degrees. So we don't have to add 180 degrees because tangent inverse gives us angles between negative 90 and 90, and that's fitting with our picture. So let's take a look at another example involving velocities and vectors. So here this situation says that a person launches a boat on one shore of a river and they want to make it to the exact opposite side of the river, and here it tells us that that's directly north. It says the speed of the boat is 10 miles per hour and the river is traveling 5 miles per hour east. And so we're looking for the direction that we should drive this boat. This person should point the boat in so that we land on the exact other side of this river. So that's a lot of information to unwind, but maybe let's just start drawing what we know. So here we know that this person is trying to end up directly north on the other side of this river. So if I draw out a coordinate plane, and here's north, south, east, and west. So here's north, south, east, and west. And maybe let's say this person is right here at the center of this plane. So here this is where the boat is, where they're going to take off from. This person wants to end up north on the other side of the river. Directly north. So here maybe I'll interpret this bottom side as the shore, it's the land, and the river is traveling here, it says 5 miles per hour east. So we've got river in between this person and where they want to end up at, but we know that this river is traveling 5 miles per hour directly east. And so this person, they want to end up directly north. They're going to travel, they're going to drive this boat in some direction. And we want to figure out that direction. But we want to figure out that direction so that after the influence of the river, we end up directly north, traveling directly north, and so they'll end up exactly on the other side. And so here, what we do know is that the boat is traveling, we don't know the angle, but we know it's traveling at 10 miles per hour. So here, if I call this vector u, then I know that the magnitude of u is equal to 10. And we know that if I call our vector v, the river, the velocity of the river, we know that the magnitude of v is 5. And when we add these two vectors together, it's going to give us the true velocity of our boat, so u plus v. And we want this true velocity vector to be pointed directly north. So these are all the pieces of information that we want to incorporate into finding the angle of our boat vector. And so let's start writing some component form vectors for u and v, so that when we add them, we can sort of try and draw some sort of conclusion about u plus v. So here, u, we don't know what u is equal to, but again, we know that u is going to have some sort of component form. It's a times I plus b times j. Oops, not green. B times j. And again, no matter what vector we're talking about, it's going to be equal to the magnitude of our vector times cosine of the direction of the vector, and then b is equal to the magnitude of the vector times sine of the direction of the vector. This is always true. And what we do know is that here, that means that u is equal to, well, here the magnitude is 10, so it's going to be 10 times cosine of theta times I plus 10 times sine of theta times j. So this is what we know about our u vector. But we don't know this angle. This is sort of the big question in our problem. So maybe let's move on from here. But we know we have some representation of this boat velocity vector. Now what about the river velocity vector? Well, here it's traveling directly east. So the vertical component of our river velocity vector is going to be 0, right? There's no vertical component to our river velocity. So this is just going to look like 5i, and maybe I'll just write 0j just to make it very clear that there's no vertical component to this river vector. It's traveling directly east. And we know that when we add these two vectors, we'll end up with the true velocity of our boat. So this is going to be, well, if we add up the horizontal components, we get 5 plus 10 cosine of theta times I. And that's the horizontal component of our u plus v vector. And if we add on our vertical components, so this is 0 plus 10 sine of theta, so 0 plus 10 sine of theta, that's 10 sine of theta, that's the vertical component of this addition vector. And this is going to be the true velocity of the boat. And so the big picture, the big idea in this problem is that we want to travel, this person wants to travel directly north. And that means that this u plus v vector, it shouldn't be moving left or right, it shouldn't be pointed left or right. The horizontal component of this vector should be 0. We're saying that in this sum vector, we want to travel directly north. This must be 0 because u plus v in our picture should have no horizontal component. Right, based on our picture, this boat is not going to travel left or right. The horizontal component should be 0. And so here, let's solve this equation. Let's figure out what values of theta would make this horizontal component equal to 0, because such a value of theta would it would be the direction in which we want the boat to travel. And so solving this equation, we subtract away 5 from both sides, divide both sides by 10, and so now we're asking what values of theta give us cosine is equal to negative 1/2. And so here, cosine being negative 1/2, this is an x-coordinate on the unit circle of negative 1/2. X is equal to negative 1/2. This happens at these two angles here, these two positions here. And so here, this is a 30, 60, 90 triangle, right? So here, if this side length is 1/2, negative 1/2, then this is telling us that this side length is the square root of 3 over 2. This is 1, and our angle here is 120 degrees, or 2 pi over 3, for this top position in the interval from 0 to 360 degrees. And we can keep going also to find that the angle down below would be, well, that would be 240 degrees. But 240 degrees in our picture would point the boat back in the direction of the shore, in the direction of the land. So our angle theta should be 120 degrees. Now, this is the value of theta that makes cosine of theta equal to negative 1/2. It makes the horizontal component of our vector 0, and so it makes this person travel directly north. This is the angle the boat should travel, is 120 degrees. So theta is equal to 120 degrees.